But the church was not comprised entirely of fools. There were people who raised scientific and physical objections to Galileo's assertion that the heliocentric model for the solar system was the only one that worked. And the most important failure of the heliocentric model was the absence of stellar parallax. And what this is, that if the Earth was really orbiting the Sun, then it's changing its position with time. And it's doing so pretty quickly. 30 kilometres a second is how fast we're going right now. That's about 100,000 kilometres an hour to get from here all the way around to the orbit and back again in only 1 year. So it should have been possible when you're making observations of the stars in January compared to June to see the nearby stars switch backwards and forwards relative to the distant stars, in the same way that if I wander backwards and forwards across the front of the lecture theatre, I see people in the front seats shift backwards and forwards relative to the back seats. And also our sensors tell us that the planet isn't moving because the curvature of the orbit is so slight. And Galileo realised that if you did an experiment in a laboratory, not with torches, clocks, butterflies and apples, but with musical instruments and balls dropped from a height and balls rolling down inclined planes, he realised the results of doing that experiment, those experiments would be exactly the same on a laboratory plunging through space at high speed. Not on a spaceship in his time, of course, but on a ship. So he says there is no difference between these two laboratories. You cannot detect the motion of this lecture theatre through the cosmos by doing experiments inside. This is Galilean relativity. Experiments with mechanics, of course. He didn't know about electromagnetism in 1634, but of course it still works with electromagnetism, but that's another lecture. And Newton realised that things continue on their way and they're subject to an external force. So there was no way of detecting the Earth's motion through the cosmos by doing experiments on the Earth or using your own sensors. Here's another example that I use in my relativity lecture. Here's a steward in a late lamented Concorde pouring a first-class passenger a glass of champagne, and regardless of whether the Concorde's parked at the gate or doing twice the speed of sound, the champagne leaves the champagne bottle and falls harmlessly into the glass. It doesn't suddenly fly back and hit the passenger in the face at 2,000 kilometres an hour when the Concorde is cruising. You can't do experiments with champagne to detect that you're travelling at twice the speed of sound if you're inside the cabin. Put your head out the window, that's a different matter. But inside the cabin, you can't tell. And so this is why you can't detect the speed of the Earth by being inside. And it's just as well because it's a bit of a scary place out there. We're plunging around the centre of the solar system at 250 kilometres a second, centre of the galaxy rather, as the Sun orbits at a speed of 250 kilometres a second, and probably the Milky Way galaxy is plunging towards the great attractor at 7,000 kilometres a second. So I think so that we can sleep well at night, it's good that we can't detect all those speeds. But the parallax problem wouldn't go away. And Galileo tried to detect parallax by making observations 6 months apart of what he thought were nearby stars. He assumed, quite reasonably, that the stars were the same as our Sun, and by looking through his telescope, he could see the disk of a star, and he didn't know anything about wave mechanics. He didn't know light was a wave, and he didn't know that when light coming from a distant star passes through the objective of his telescope, that it undergoes a process known as diffraction, and so instead of seeing the shadow of a pinhole corresponding to the image of a distant star, you see a diffraction pattern. A large disk surrounded by rings of diffracted light. So what he was seeing in his telescope and from his sketches was not the real size of a star. And so he calculated for this double star Mizar, which is located near the North Celestial Pole, and they're the best stars to look at. He calculated that this double star, the bright one and the dim one, were 300 astronomical units away, 300 times the distance of the Sun from the Earth, and 450 astronomical units respectively. And he figured that over the course of a year, given the diameter of the Earth's orbit, he should have expected the view of the two stars to change as the Earth moved backwards and forwards. And he watched this star for years. He never saw the two stars move at all. And he never published it, that failure to detect stellar parallax, which would have proved the heliocentric model once and for all. The technology for detecting the very slight stellar parallax, the universe is unreasonably large. The true distance of these two stars is more than 5 million astronomical units, for which the diameter of the Earth's orbit is entirely insignificant. Didn't occur for several hundred years later. And in fact, it isn't even the biggest phenomenon that caused stars to shift backwards and forwards. The changing velocity vector of the Earth, changing directions, has a bigger effect. Or you can just take a spectrum from the cosmic microwave background, and sure as hell that was beyond the technology of the 17th century. But I don't want to go into that. So with all these observations, apart from the failure to detect stellar parallax, we can now evaluate Galileo's legacy. So in the words of Sir Henry Wotton, from the strangest piece of news ever yet received from any part of the world, the author has certainly runneth a fortune to be exceedingly famous, not exceedingly ridiculous. So here we have Neptune now. Viewed in close-up from the Voyager space probes, officially discovered in 1846 by telescopic observations, guided by theoretical predictions from the mathematicians using Newton's universal gravitation. This was the first planet discovered by the point of a pen and not by a telescope, or at least predicted by mathematicians scribbling in notebooks, from the perturbations of the orbit of the other planets. Or, ladies and gentlemen, was it really discovered in 1612? Now, how would one prove that Galileo knew he'd discovered a new planet? You can imagine how rapt the gentlemen of the Inquisition would have been if Galileo had said, and by the way, I've also discovered a new planet never seen by humanity before, not mentioned in any of the received wisdom. I imagine they would not have been enthusiastic. Furthermore, if the planet is too faint for the eye to see, how would you pick it up again after it had drifted away from Jupiter? You would never find it again in the sky with a Galilean telescope with a narrow field of view, and without Newton's universal gravitation, you could never predict its orbit from the observations. But ladies and gentlemen, I'd like to put it to you that there is a way. Let's go back to January the 6th of 1613. Back to his notebook as it appears on the web. In my view, Galileo made the observations where he saw Neptune move in late January of 1613, realised he had seen a new planet, and flipped back through his notebook to the night of 1612. The intervening nights were cloudy, observations were not possible. It's winter, remember, in Florence, and believe me, it gets jolly cold over there. And he made a mark in his notebook where he recalled seeing Neptune on that previous observing night. He didn't get it in exactly the right place, as my simulation showed, because he was only putting the dot in from memory. And he didn't label it possible new planet, because it would have got him into big trouble, and he didn't have any way of proving this to somebody else once it had drifted out of the field of view. So in my view, this dot that he made in January the 6th will have an ink composition consistent with the ink he used on the night of January 28, and not consistent with the composition of the ink he used in January 6th. He made his own ink. The composition varies randomly from night to night. And fortunately, my colleagues at the University of Florence in the Department of Physics have a nuclear particle accelerator, just like the one I have in the basement here, where they can bombard Galileo's manuscripts with beams of protons and fluoresce X-rays from the ink. And the X-rays tell you the trace element composition. And they've already done this on undated manuscripts of Galileo in order to find the date at which they were written, to settle disputes about the development of theories of mechanics. So they have a database of compositions of Galileo's inks. So when I went to Florence in December last year, I asked them whether this would be possible. They got wildly excited. The only slight difficulty is the librarian. The librarian is not enthusiastic about physicists coming down to the library, borrowing Galileo's original notebooks and putting them in front of the business end of a nuclear particle accelerator. And I don't know whether I triggered this, but the librarian immediately took the notebook that has this dot in it and put it on display for the International Year of Astronomy in a locked, sealed cabinet with alarms on it and not to be removed until the end of the year. But I hope we'll lose interest, but we won't. My colleagues in Florence will be standing by when the exhibition closes to borrow the book and take it back to the lab. Because if this ink from the dot is really that of January 28, then I think that shows Galileo knew what he had discovered, the first new planet since deep antiquity. And so I said at the beginning that Galileo stands at the boundary between the medieval world, the world of received wisdom, and the modern world where you see for yourself. So if there was a time where we have to put that boundary, if there was a year, I would say it was 1613. If there was a month, I would say it was January. If there was a date, I'd say it was January the 16th. And if there was to be a time, I would say it's the time where Galileo lifted his pen from the page after making that mysterious black dot. There ended the medieval world. There started the modern world. But it's only one tiny black dot. You might put the proton beam on it and you might blow it away. That would be very disappointing. So is there something else still buried in Galileo's notebooks that could be irrefutable evidence of a new planet? Well, I promised you 3 anagrams. I would put it to you, ladies and gentlemen, that waiting to be discovered in Galileo's voluminous literature, there is a 3rd anagram waiting to be decoded. And naturally, I've been surfing the web continuously looking at Galileo's notebooks. They're all in Latin in appalling handwriting, looking for a string of meaningless characters written sometime after January 6th of 1613. I have not found such an anagram. So I've had to make one up for myself. So here is my concluding slide and my 3rd anagram. Is there a hidden 3rd anagram? Here it is. Oblivion valens tamen pavor, which translated means I boldly follow the path even though scared. But ladies and gentlemen, I'll put it to you as a competition. Please email me what it really says and see if you can decode my anagram. I'm Galileo, you're Kepler. Ladies and gentlemen, thank you very much for your attention. Now, I'm conscious of the lateness of the hour, but I think I'll take just 3 quick questions, and you're welcome to come down and have a look at some of the gear up close afterwards. So, does anyone have a pressing question? Yes, gentleman up the back there.
Surely it's a particularly big call, either on your part or Galileo's, that a dot one night is the same object as reappears sometime later.
Yes, it's a big call, but Galileo was a smart guy, and he often wrote down observations from memory that the computer simulations verify. So, for example, when he made the note that the object B appeared to move relative to the object A, he hadn't actually recorded an observation the previous night, so he was making that observation entirely from memory. So he was a very acute observer, he had a very acute memory. Gentleman down the front.
He tried to create a greater than 20 times or so. How long was before that actually started creating telescopes of a better magnitude?
Well, that's a good question. I guess I don't know the answer, but it might have been 20, 30 years or more after Galileo, because there was suddenly a huge driving force to perfect the telescope with this avalanche of new discoveries. So the lens grinding techniques had to improve, the clarity of the glass had to be improved to blow all the iron out of it, to make it clearer, to get the bubbles out of it, so the image wasn't all distorted. I think more than 20 years, because I know Galileo was still the best lens maker for more than 20 years after 1609. But then of course the lenses grew bigger and bigger, heavier and heavier, and eventually when Newton came along, blew it all away and they were replaced with mirrors. And they were the ones that, of course, what modern astronomers use. One final question from over here. Did Galileo's maid ever write anything about him? Well, we're now entering domains where I'm not well qualified to comment, but I can say that Galileo remained on very good relations with his maid. He took custody of the 3 children because they were illegitimate. Their prospects weren't good, so he put the girls into convents, and he eventually he legitimised his son, and his son then went on for quite a promising career. His wife later, his housekeeper later married, and someone else obviously, and Galileo remained on cordial relations with the married couple after they separated. So I think what was the question again? I don't know. There was a lot of literacy around in those days. You know, professors of astronomy were literate, but I don't know how many other people were. Not too many by all accounts. Maybe one final question. That wasn't a scientific question. I had to speculate a bit. Okay, right over there in the aisle. Yeah.
So how did Galileo reconcile the lack of observed parallax with his theory that the Earth around the Sun? Like, what was his own explanation for it?
He just didn't publish it, so that was how it was. No. It's interesting, the history of the attempts to measure the parallax of the stars. It had already been suggested before Galileo that if you wanted to check the Copernican theory, then you should look at the parallax of the stars. And a suggested method was to find a hilltop in somewhere that had a church on the top of it with a plain, a distant plain. Now, church, hilltop in Italy, no problem at all. Distant plain, you nail a bit of wood to the steeple of the church, and you stand on the distant plain and you watch the stars go down across the bit of wood and look for changes in their position with observations made 6 months apart. This was the first method that was put forward that people tried but didn't see anything. The second method was Galileo's method of finding a double star above the North Pole, where the effect is most extreme, and making careful observations over the years. There was a theory put forward when no one found this, with the naked eye observations, that maybe the stars were too far away, that the orbit of the Earth was insignificant. But that was rejected as clearly ridiculous, because that would make the universe, you know, unreasonably large. Well, sorry guys, that was the right answer. All right, folks, I'm conscious of the time, so thanks again. Please keep an eye on the follow-up lectures in our program, 4 more to go, and this special extra lecture that's being presented in conjunction with the annual meeting of the ASA, the Astronomical Society of Australia, which is next Monday night. All these lectures will be at 8 o'clock in here at the Elizabeth Murdoch Theatre. Thank you very much for coming.